So any wave can be made to form a standing wave. We've seen this for waves on a string, but you can also do this for sound waves. And our simplest form for containing a standing sound wave is a simple tube. Now this is an open tube because it's open on each end. And the wave that forms inside of this tube, the fundamental mode, is a node on either end and an antinode, a single antinode inside. And it's a node on either end because sound is a pressure wave, so it travels by variations in the air pressure. But the open ends are open to atmosphere, so the ends are at atmospheric pressure. They're fixed there. But inside of this tube, the pressure can oscillate up and down. And so that's what we get here. And you can actually hear this fundamental frequency if you have a tube and you just, an open tube, and you just hit it. In fact, there's a toy called a boom whacker that does just that. Here's an example of that.
1, 2, 3.
Fantastic. So not only is that a good demonstration of the sound that an open tube can make, it also is verification that socks and sandals is still a thing. So so what we were hearing here were the fundamental frequencies. But you can actually get higher frequencies. Oops, let's change that back to what. You can get higher pitches by accessing more than just the n equals 1 mode. The n equals 2 mode has a single node in the middle. Oops. All right, and so that standing wave would look like this. Again, it's node on either end and a node in the middle. That's n equals 1, sorry, 2. And n equals 3 and n equals 4 are fairly similar, right? So there's a node on either end. For n equals 3, we have 2 nodes in the middle, and the wave would look like this. And for n equals 4, there's a node on either end, and there are 3 nodes in the middle. It's not quite evenly spaced. If I can fix that. That's better. And then I missed the node. It's fine. You get the idea. Okay. So I want to point out that this is exactly like what we saw for a standing wave on a string. Right? These are exactly the pictures we drew for a standing wave on the string. So the math that we built up for that is identical to this. Right? So if this is a length L, I can relate, let's make this go away. I can relate wavelength and the length of this tube the same way. Right? So lambda sub n is 2L over n. And the frequency f sub n is n times v over 2L, also n times f1. Okay, so how do we access the higher frequencies? Well, if you've ever seen a whirly tube, Let's head back to YouTube. Here's an example of these whirly tubes in action. See right there, right there. The guy in the middle swung the whirly tube a little faster, and he accessed a higher harmonic. Right, same length of tube, just whirling it faster, and you get a higher harmonic. So this is a really cool application, or a really cool use of these essentially child's toys. So that's really interesting. I want to show you another system, though. I want to show you two more systems, actually. You can also have, say, a closed system. So what does a closed system look like? This would be a closed system, and you could maybe excite this motion by maybe cutting a small hole right here and blowing across that or something. So this is a closed system. What would a standing sound wave in a closed system look like? Well, the closed end would be a place where air could rush toward it and away from it. So in that way, when air is rushing toward it, that's a higher pressure. When air is rushing away from it, that's a lower pressure. So the ends are antinodes. Right? So what's the lowest frequency, the lowest mode that we can put in there? Right? Another way you could drive this is by putting a speaker inside of there and driving it with some frequencies and then hearing which ones are loud. So here's what you can do. This side is going to be an antinode, and this side's also going to be an antinode. And you have to have at least one node in the middle. So that's what's going to happen here. Is there's a node in the middle. And this turns out to be the lowest mode. And then you could do another one, right, where maybe there are two nodes in the middle. So that would be like right here and right here. And again, the ends have to be antinodes. So that would look like this. And I'll draw two more. The ends are still antinodes, but now I've got three nodes in the middle. So how do I put three nodes? It'd be probably like this. And we'll do one more, and then we'll talk about this mathematically. So now I need to put four nodes in there. So four nodes might look like that. Okay, fabulous. So if we look at the first mode here, it looks like it's the same thing as the picture on the right, but it's like we cut it in half and took one end and stuck it on the other end. Do you see that? And it's the same thing on the second bit. If I take this end and shove it over here, that's the same as this. So so we're really accessing exactly the same modes here. And so my argument is this: for a closed system, the math is the same. All right. Oops, I went a little too far. think. Why did my green one go away? There. Fine. So the math for open, open, and closed, closed systems, both of them follow this math. But you can imagine one more system, which would be an open-closed system. What does that look like? Well, an open-closed system looks like that, right? I've got an open end over here and a closed end over here. So let's draw the first few harmonics for this. So this side, the closed end, has to be an antinode, and the open end is going to be a node. So we could draw this. There's our lowest frequency or longest wavelength, right? What you can notice here is if this tube still has a length of L, the wavelength here is 4 times L, right? Because this is only, that much is only half a wave, right? That's a half of a wavelength, which means this is a quarter of a wavelength. Or if L equals a quarter lambda, then lambda equals 4L, which is why I wrote that. Okay, so let's make some of this go away. How much can I make go away? Perfect. Okay, so we can draw another one. That's maybe a little big, but who cares? So again, that side's going to be an antinode. If I'm not careful, I think maybe I need to put those backwards. Let's put the green one up here, and the blue one down here. And then I'm going to have a node at this end and another node in here, and that second node needs to go like right here, I think. Okay, so this does this, and this does that. Now what do I have in here? That's 3/4 of a full wave, right? So if L equals 3/4 lambda, is that right? No. If yeah, if L equals 3/4 lambda, then lambda equals 4/3 of L, right? And that makes sense. Lambda is just a little longer, right? The rest of it is right here. Okay. Let's do maybe 2 more of these, and then we'll be able to come up with a general rule. So still have a node over here, and now I'm going to need 2 nodes in the body of this. That's pretty good. It's not the best thing. It's not terrible. Oops. Okay. So now it looks like there's 5 quarters, right? Because this much is a quarter wave, and this much is a whole wave. So the total L equals lambda plus a quarter lambda, which is 5/4 lambda, which means that lambda equals 4/5 L. And you might be able to see the general rule, but we'll do one more, and then we'll write the general rule for this. Okay, so one more. A node at this end, and instead of 2 nodes inside, I need 3 nodes inside. So there's 1, there's 2, there's 3. That's not spaced well, though. That's a little better. Not perfect, but it doesn't have to be super pretty. I am going for a little better than that, though. That's okay. Okay, so what do I have here? Well, again, that last little bit here, this bit, that's a quarter, and this is a full wavelength. This is a half wavelength. Half wavelength, and this is a quarter wavelength. So L equals lambda plus half lambda plus quarter lambda. So what does that work out to be? That's half is 2/4, oops, and 1 whole one is 4/4, so it's 4, 5, 6, 7. 7/4. Right? You can count them, right? Here. 1, 2, 3, 4, 5, 6, 7/4 of a wave in that. Make them all go away. Come on. 7/4. Which means lambda equals 4/7 L. Okay, so now we can look at these numbers and see, well, look, it looks like my general rule is going to be 4L over N. But N is now just odd numbers. You see that? 4 over 1, 4 over 3, 4 over 5. So lambda sub N is 4L over N, where N equals 1, 3, 5, 7, etc. So that means that these wavelengths are spread out in a different way than it is for an open-open or closed-closed system. It also means that an open-closed system can reach a lower frequency or longer wavelength than an open-open or closed-closed system of the same length, right? Because that was lambda sub n is 2L over N for an open-open or closed-closed. Okay, so we could do one more thing here and then maybe do an example. The frequency here is going to be N times V over 4L, where again N equals 1, 3, 5, and so forth. So again, we're dividing by 4 instead of dividing by 2. Otherwise, the expression is the same as for open-open or closed-closed. So an open-closed system can reach a lower frequency for the same length of tube. Okay, just for example, brass instruments are open-closed systems. So, and actually you can picture, if you've ever played a brass instrument, you can use the same length of tube, right? So if you don't push any valves down, you can use the same length of tube to reach all sorts of notes, right? So on a trumpet, like low C is open, and then middle G is open, and then high C is open, right? And all you're doing is changing how you're vibrating your lips. You're changing how you're exciting that mode. So if you excite with a frequency that is close to one of these resonant frequencies, you will you'll hear that, right? It'll be louder. Let's do one example. So the contrabassoon is a wind instrument capable of sounding the lowest pitch in the orchestra. It's folded over several times to fit its length of 18 feet into a reasonable sized instrument. If we model the instrument as an open closed tube, what is its fundamental frequency? So I want to know, what is F1? Let's take the speed of sound to be 350 meters per second. Okay, so that's just plugging into the math here, right? So 18 feet, what is that in meters? Turns out to be 5.49 meters. So what is that frequency? Well, we have options. Let's do wavelength first. So lambda 1, lambda sub n, right? We just found lambda sub n is 4L over N, where N equals 1, 3, 5. If we're just going for 1, though, then I just need 4L, right? So lambda 1 is 4L, or 5.49 meters times 4, which is 21.9 meters. That's the wavelength. And then frequency, remember V equals lambda F. And in this case, we're going to do lambda 1 F1. Again, I can't mix indices. It's got to be 1s or 2s or 3s. This case, it would be 1s or 3s or 5s. Okay, so plugging into that, it's 350 meters per second equals 21.9 meters times F1. And if you do that math, what you get for F1 is 16 hertz, which is really low, right? You may not even hear that well. You would actually just feel it. So that's interesting. Another application for these is pipe organs, and we'll see that in a future example.